Okay, now we can start.
So the electrochemistry is an important subject, and in this, in the electrochemistry there are three various branches dealing with ionics, Debye theory, and other things, conductivity and other things that we are not going to deal with it. We are going to only deal with the electrodics, that is electrode electrolyte interface. So what is the essentially what we are going to cover? Okay, we are going to cover only electrodics part of alone will be covered. Ionics will not be dealt with. What is electrochemistry? How this subject is useful in energy storage devices, delivers energy at will. This is because the chemical reactions are generating the electricity here in the electrochemical cells. So therefore, as you all know, as chemists, we are only worried about the electrons and how these electrons are ejected out or taken up by chemical entities. That is what is the chemical reaction. So these electrochemical cells also deals with the ejection of the electrons and the acceptance of the electrons. So therefore, there is various types of electrochemical cells, and there are various notations to be followed. We will as we go along, we will see the types of these cells and the cell potentials and the rationalization of these cell potentials and half cell reactions. Now, in doing this, we have to understand the electrode electrolyte interface. We will deal with the metal solution interface, which is the main basis of electrochemistry. But as we all want to know semiconductor solution interface, so therefore in our photoelectrochemistry, it is really semiconductor electrolyte solution interface. So we have to do a small change, or not a small change, it is a major change as compared to the metal solution interface. We will see that. The electrochemical cells are also energy storage devices. Now, there are three ways of energy storage. As we all see that electrons are the main chemical entities. Now, when we use the electrons as the main chemical entities for energy, then there are three devices. One is the batteries, another one is the supercapacitors, third one is the fuel cells. Now, batteries and supercapacitors are energy storage devices, whereas fuel cells are energy sources directly. As long as the fuel is fed to that, it will generate the electricity. But anyway, the chemistry of them, whether we are storing it as chemical species in the batteries and supercapacitors, or as use a fuel to combust the fuel to get the electrons out, there are also the energy conversion devices. Now, when we take the electrode reactions, we will see later on, electrode reactions, they are governed by certain signs. Okay, these are all going with the name of Butler-Varma equation, Taft equation, and all those things. Therefore, these are all general principles for applicable for all electrochemical processes. We will be dealing with them also. Now, quickly looking at electrochemical cells, chemical energy is converted into electrical energy. That is all the thing that is happening. Now, what is the chemical energy and how it is converted to a electrical energy? So therefore, that means we have already seen in the electrochemistry, what happens here is the chemical species either gives the electrons or receives the electrons. So therefore, reduction, oxidation reaction has to take place. So therefore, this is spontaneous. If the reaction is spontaneous, the reduction or oxidation reaction is spontaneous, then it will be generated a voltage or electricity. So we will see that. The oxidizing and reducing species have to be separated because the same electrode, it cannot take place. Force the electrons to travel the through a wire. There is a logic that we have to understand. The electrons in all these electrochemical cells flows through the outside the electrochemical cell by the interconnecting wire. Inside the electrochemical cell, the ions are moving. So this is a very important parameter that we have to understand. Electrons move in the outside circuit, ions move in within the circuit. So now if I were to take an electrochemical cell, I hope you are able to see the picture. So therefore, an anode and a cathode. Okay, the cathode, the reaction that is taking place at the anode is the oxidation reaction. The reaction that is taking place at the cathode is the reduction reaction. If the solutions are going to be different, then we should interconnect them for the ion transport by a salt bridge. Now here is the voltmeter or ammeter, whichever you can't say. You can see that the electrons are flowing in the outer circuit, ions are flowing within the circuit. Now, when I take a zinc foil or zinc electrode and put it in a zinc sulfate solution or zinc nitrate solution, then the zinc will dissolve into zinc 2 plus, and the two electrons will go in the outside circuit, and use the cathode. The two electrons will combine with the copper sulfate solution in the copper sulfate or whatever copper 2 plus ion. The two electrons will then precipitate or deposit copper. Okay, this is the principle of the electrochemical cell. Now we have to understand few things. Which is the correct way? Whether zinc will dissolve as zinc 2 plus or copper 2 plus will deposit as copper, or copper will dissolve as copper 2 plus and zinc will deposit as zinc 2 plus will deposit as zinc. This is a very tricky question. We will come to it. A voltaic electrochemical cell may be represented by the following. Here it is done in a clumsy way, but anyway, a zinc electrode dissolved in zinc sulfate or zinc nitrate solution, and that salt bridge is shown here. Then copper 2 plus is in solution, deposits copper. Okay, this the lines must be are not aligned here, but doesn't matter. A single line represents phase boundary. For example, zinc is solid, zinc solution. Okay, solid anode to a 1 molar liquid solution, and the double lines represent the salt bridge. The standard conditions that we are taking, we will see later on why the standard condition and the things is 25 degrees C, 1 atmosphere, and 1 molar solution. Okay, we will see later on what is the 1 molar solution and why 1 atmosphere and all those things, because it can be a hydrogen evolution reaction and all those things. So therefore, that should be under standard state conditions. That is one reason. Then in the Nernst equation, we have to substitute RT by NF. So we should know all these parameters. We will see later on all those things. The cell potential is the ability of a cell to do electrical work. Okay, each cell is measured in volts. 1 volt is 1 joule coulomb. Please remember this. These are all very important parameters for us, because later on we have to look at it. When we put RT by NF, we have to use R in the joules coulomb thing. The FF is in coulombs, therefore the unit will be volts. That is why it is coming in that. In the Nernst equation, E is equal to E0 minus RT by NF. R has to be in joules. Where coulomb is the quantity of charge passing in 1 second when a current of 1 ampere is flowing through that. 1 coulomb is 1 ampere per second. Okay, so coulomb is 1 ampere per second. So we will have all these units later on, because these are all must be very clear to us, so that later on we will be able to use them. Standard reduction potentials. Okay, this is one of the bugbear for all of us, because there are so many standard electrode potentials. How to remember them, and I think we will see a very convenient way of remembering them. We will come to that really in a minute. Most reference tables for electrochemistry are written as reductions in a half reaction format. Reduction reaction only is written with the most negative reduction on the top and the most positive on the bottom. Okay, I will tell you what this means. This is going to be a totally new notation. You have to learn this, By definition, all half cell reactions are compared to the hydrogen half cell reaction that has standard value of 0 volts. So therefore 2H plus plus your 2 electron giving rise to H2, that is called the 0. So when we take the line, I will show you in a minute, all other reduction potential are based on this 0 point. So therefore you can see the positive value F2 is the, I hope you understand, the fluorine plus 2 electrons. Fluorine is the most electronegative element. Two electrons it take, then it will become 2F minus. So this is given plus volts. Why plus volts is the question. Okay, I must tell you. The plus means E is plus, delta G is minus. So the delta G is equal to minus NFE. When E is positive, delta G is negative. So therefore what it means is the fluorine capturing 2 electrons is a spontaneous reaction. The same way, lithium plus electron giving rise to lithium solid is minus value. Okay. Whereas when you take lithium, the spontaneous reaction will be lithium plus, because lithium plus is the stable species, closed shell configuration. So therefore, this is the reduction of lithium plus electron giving rise to this is the minus potential. Okay, I hope you understand this. These two are the two extreme cases. In the whole of the periodic table, all other potentials must be in between them only. Okay, so therefore, what it means is lithium plus electron giving rise to lithium. Therefore, it is a strongly reducing agent or easily oxidized. Okay, lithium is easily oxidized to lithium plus. Fluorine is easily reduced or strong oxidizing agent. It oxidizes, easily reduced or strong oxidizing agent. Okay, we will see later on. All these things are very important for us when we have to do electrochemical redox reaction. So now what it means is all our potentials have to be either plus 2.86, let us put plus 3 volts and minus 3 volts. So all the other potentials must be in between them only. It cannot be different. Okay. So now let us take it a little bit better and do this in a very systematic manner. So rules for using standard reduction potentials is read the half cell reactions as written. The more positive the reduction potential, the greater tendency is for that substance to be reduced. Therefore, they are better oxidizing agents. Keep the Hobbes reaction with more positive cell potential as written in the table, that is the reduction reaction. The half cell reactions are reversible. If you need to reverse, you must change the sign of the E0 per cell. If you change the stoichiometric coefficient, E cell remains the same. Okay, that is it. That is the 1 electron or 2 electron. It also will be the fluorine reduction reaction will be giving you plus 3 volts only. That is what it means. So now we are going to see under standard state conditions, any species on the left of a given half cell reaction will react spontaneously with the species that is on the right side. So now if you look at the left hand side, the zinc will get dissolved and copper will get copper 2 plus ions will get deposited as copper. The half cell reactions are reversible. If you need a reverse, you must change the sign of the E0. The most positive values of the E cell mean that they are strong oxidizing agents and therefore are themselves reduced. The most negative values of E cell means that they are strongest reducing agents and therefore themselves are oxidized. The total potential is simply E cell is equal to E oxidation plus E reduction. E cell means the reaction will happen if E cell is positive, then a positive E0 means spontaneous reaction. A negative cell means the reaction will not happen. What will be the overall reaction and the E0 cell total if bromine is added to a solution containing iodine at 25 degrees C? Assume all species are in the standard states. So off-cell reaction is I2 solid plus 2 electron giving rise to 2 I minus. E cell is 0.53. Bromine is liquid plus 2 electron giving rise to 2 Br minus. Okay, it should be Br minus plus 1.07 volts. So using the standard reduction potentials, the fact that bromine has a more positive potential indicates that the bromine will be reduced. So change of sign of the oxidation reaction, and so the reverse. So it will be written. It is written as oxidation reaction. So Br liquid plus 2 electron giving rise to 2 Br minus. The minus is missing here. The E reduction is plus 1.07. 2 iodine giving rise to iodide ions giving rise to I2 is the oxidation reaction. So therefore the cell potential will be 1.207. We are now reversing this, therefore minus 5.3. Therefore the cell potential is simply the difference of this. This is the only one example that we have shown. So now this is what I said, that we are going to use a nanogram where we are going to put, I hope you are seeing it. So the positive potential is put in the fourth quadrant. The negative potentials are given in the first quadrant. Okay, so this is the first quadrant. This is the fourth quadrant. You must understand why first quadrant and the fourth quadrant. This is all positive values, positive values in the fourth quadrant and the negative values in the first quadrant. We have already told, when the potential is E is negative, delta G is positive. Therefore, the first quadrant is positive delta G. The fourth quadrant is negative delta G. That is why we are using the voltages as the first quadrant negative voltages, fourth quadrant is the positive voltages. So now look at these two tables. Okay, these two tables are all the values that are given. We will have a very small discussion here to remember all these numbers. Okay, you need not remember absolute numbers, but at least the magnitudes of this. We have already seen that the highest positive value is fluorine getting reduced to fluorion, plus 2.87. The negative value, the highest negative value is lithium plus ion plus electron getting lithium ion getting reduced to lithium, that is minus 3.05. So these are the two things that we have put. This is the lithium ion, this is the fluorine giving rise to fluoride ion. And then the central point is the zero value, which is the hydrogen reduction potential. Okay, so now it is very clear to us that all of my positive values must be here, all my negative values must be here. Okay, so now let us take a simple example and then do that. For example, you take a potassium, sodium, lithium. Okay, all of them are very similar. We have to take the lithium plus potassium plus electron, or sodium plus electron. All of them will be around 3 volts, minus 3 volts. For example, potassium is, if you look at these values, potassium, if you look at the value here in this table, okay, potassium has got a value of 2.93 and sodium has got a value of 2.71. Okay, potassium has got a value of 2.93, sodium has got a value of 2.71. So it is all around, you can see around 3 volts is the thing. Then in the same way, if I were to take a second group element, like magnesium, barium, calcium, strontium. Okay, uh, magnesium is 2.3 minus 2.37. Barium is I hope you are able to see bariums in this table. Calcium is here, is 2.87. Barium is 2.90, and strontium is 2.89. So you see, whichever species is very close, the first row element and second row element will have more or less similar potentials. I hope you are able to see them. The same way, if I were to look at the fluorine, you look at the chlorine. Chlorine is 1.36, and bromine is 1.07 plus 1.07, and iodine is plus 0.5.3. Okay, so in this case it is 2.87, 1.36, and 1.07 and 0.53. So in this case the positive values are, as the electron affinity is decreasing, it is also decreasing this. So therefore what it means is, I hope you are understanding is, that in all the cell potentials you will have around, if it is a first group element or second group element, it will be around -3 volts for the sodium, potassium, lithium, and magnesium, strontium, calcium, and things. All other things will be uh, half of it or something like that. So therefore if we take this thing, the battery can be only using these redox reactions. Therefore the maximum voltage that we can get is of the order of, except in the case of lithium batteries or alkali and alkaline earth batteries. Other than that, all other batteries should give you less than 2 volts. Common alkaline battery is 1.5, lead acid battery is 2. Okay, calculator mercury battery is 1.3, and then okay. So now if delta G0, that is the standard state conditions of free energy change, is less than 0, it is a spontaneous reaction. If it is greater than 0, it is not a spontaneous reaction. If it is equal to 0, it is an equilibrium reaction. So therefore E cell E0, the standard cell potential interrelationship between delta E G0. Okay, delta G0 is minus NF E0. So therefore E0 is positive, means delta G is negative, therefore spontaneous. If delta G is minus RT ln K, so K value also is controlled. K is the equilibrium constant. When delta G is negative, K is greater than 1, or E cell is less than 0, or negative values. When the delta G is equal to 0, K value is 1, E0 is 0, therefore at equilibrium. When delta G0 is created for positive, when delta G0 is positive, the K is less than 1, and E0 is less than 0, negative value, so non-spontaneous. So therefore here we have the same nomogram we are using. This is a nomogram of ours. So therefore there is no name for this. This is only to show you how to remember all these numbers. I hope you have already shown this. All alkali and alkaline metals will be somewhere here. All the halogens will be spread in the positive values. And the other things, iron is 0.77, like that we can do that. Okay, so therefore what it means is, in electrochemical cell, from the anode electrons are flowing to the cathode, current is flowing in the opposite direction, because the electrons are negatively charged, current is positively charged. So this is a very simple designation. So therefore, in the anode, therefore oxidation will take place. Anodic oxidation, cathodic reduction. You have to remember this. You cannot change the reaction in the electrodes. So hydrogen, if you put hydrogen in the anode, it will give the hydrogen ions, and in the cathode, oxygen will be reduced to water. Okay, so two electrons are going to be going to the cathode from the anode. Therefore, it all depends upon whether you are looking at the hydrogen evolution reaction or oxygen reduction reaction. So electrochemistry is defined as the branch of chemistry that examines the phenomena resulting from combined chemical and electrical effects. The electrons are combining them. This field covers electrolytic processes. We are going to see this, what is meant by electrolytic processes, reactions in which chemical changes occur on the passage of an electrical current. Electrolysis. For example, if we take two electrodes and put two inert electrodes and put it, we will see what is inert electrode and things little later. Two platinum wires on a water solution or aqueous solution, then hydrogen and oxygen will be evolved. Galvanic or voltaic processes, chemical reactions that result in the production of electrical energy. So this is what we are going to see mainly of galvanic or voltaic devices. An electrochemical cell types consist of two electronic conductors, also called electrodes, and ionic conductor called an electrolyte. That is all. The three component system, two electrodes. Both the electrodes can be the same metal, or an inert electrode, or an active metal means it will be different, zinc and copper. An ionic conductor, which is a solution containing ionic solutions. Charge transport in the electrodes occur via motion of electrons. Automatically the ions are moving, therefore are holes. Charge transport in the electrolyte occurs via motion of ions, positive or negative. At each electrode, an electrochemical reaction occurs. This reaction is called half-cell reaction. Each electrode. Since there are two electrodes in a typical cell at which reactions occur, that is why it is a complete term. The overall chemical reaction of the cell is given by combining two individual half-cell reactions. There are two fundamental types of half-cell reactions. One is we saw when I took zinc, the zinc was getting oxidized at the anode. Yeah, so therefore zinc was oxidized to zinc 2 plus. Copper 2 plus ions are getting reduced at the cathode. So therefore oxidation reaction and reduction reactions are taking place. Now these are all simple examples. We are going to take few complicated situations a little later. A reaction is classified as oxidation or reduction depending on the direction of the electron transfer. If the electron is removed, then it is oxidation. If the electron is accepted by the species, it is reduction. So here we are showing this pictorially what is happening. Okay. Now we will see this situation. We have already seen that the potential on the first quadrant is negative. The potential in the fourth quadrant is positive. The same notation we are following this here also. This must be very clear to you because we are going to use this endlessly. So now, if A picks up an electron, okay, A minus. This is a reduction. This is a reduction reaction. A gives out an electron. A becomes A positive. So therefore, you can see that the electron, okay, I hope you are able to see A and B. You see A and B. The solution vacant molecular orbital, occupied molecular orbital. Okay. So now if the solution, if the electron is going from the electrode to the solution, then A minus will be formed. If the electron goes from the solution to the electrode, then A plus will be formed. Now, what is shown here, I hope you understand this. These are all atomic orbitals or molecular orbitals of the molecule. But what we are talking about is the electrode is not a molecule. It is a continuous system. That is why we are showing it as a single line. That means up to this line, the electrons are filled up. Okay, energy level of electrons here and here. Okay, so therefore the electrons are filled up here. Therefore, electron is transferred to the electrolyte, or from the electrolyte, electron is transferred to the electrode. Okay, so therefore this is the reduction reaction, this is an oxidation reaction. So involves the loss of an electron, involves the transfer of electrons from species to the electrode, or gives rise to oxidation species plus one electron. Oxidation is an energetic process and occurs when the energy of the electrode dips below the highest occupied molecular orbital of the compound. See figure B. Okay. Reduction involves the gain of an electron, involves transfer of electrons from the electrode to the species, oxidized species plus an electron giving rise to. Reduction is also an energetic process, occurs when the energy of the electrode increases above the lowest vacant molecular orbital of the compound. See figure A. Okay. So these are the two notations. So in the example that we have taken, zinc and copper metals placed in a solution of their respective sulfates and separated by a semi-permeable membrane. Then through the membrane, the ions are transported. So sulfate is transported here. The zinc 2 plus is dissolved here. Therefore, the zinc sulfate solution will form copper 2 plus ion will get deposited as copper. So zinc metal gets oxidized, goes into solution as zinc 2 plus 2 electron. The 2 electron is now going on the external circuit to the copper electrode. Copper ions in solution reduce, copper metal deposited on the electrode. Electrons for the reduction obtained from zinc 2 plus electrode, external wire. Sulfate ions, reaction 4, migrate through the membrane, react with the zinc ions to form the zinc sulfate. This is how the reactions are there. The convention is, okay, electrode at which the oxidation reaction occurs is called the anode, anodic oxidation. Electrode at which the reduction reaction takes place is called the cathode. Thus, in the above example, the zinc electrode was the anode and copper electrode was the cathode. Okay, this is the explanation, that is what is given. Why negative in the first quadrant, or why above zero all negative potentials are put, why below zero all positive potentials are put. Negative EMF means positive free energy and hence negative scale. Negative EMF, positive field, therefore free energy only is what we are plotting, or what we have to consider. That is why in the positive potential which is given from zero, below the zero, okay, in the chart, these are all negative values. These are all negative values. These are all positive values. The positive value here means the free energy is negative. Here the negative value is EMF means free energy is positive. So therefore we are plotting free energy, but since we are directly plotting the voltage, we are plotting above zero all negative values of EMF, below zero all positive values of EMF. I hope you understand this. This is a very important thing for us. We are going to use this endlessly in our discussion, because we want to remember, because we cannot remember all these numbers. We have already told how to remember these numbers. It is this is a endless table. So therefore we have to, here only we have given two standard electrode potentials, but we have to look at for non-standard conditions. We will see all those things later, but to remember them and put the approximate values, we have to remember this notation. So therefore positive values in the fourth quadrant means negative free energy, so spontaneous process. For negative potentials in the first quadrant, that means positive free energy, hence non-spontaneous process. So now we will stop at this point and answer any questions you have.
Hello, sir.
Yes.
So good evening, sir. Sir, in there is a slide where potential energy is given when electron is transferred from the electrode to the electrolyte. What will be the trend in the potential energy, whether it will increase or decrease? Could you explain it once again?
This figure you are saying?
Yeah, yes, sir, this figure.
This figure is only a representation. It is not it's an electrochemical cell.
Okay.
What it means is how when the electron will